Hello, friends. Here we are in Unit 8, the last unit of Algebra 2. It is kind of split up into exponential and logarithm functions. So we're going to start off today with exponentials, which is something that you should have seen before, I believe in Algebra 1. So you should recognize kind of where we're starting in this unit with our transformations and what the parent function looks like and how we transform it and find all the characteristics of it. That hasn't changed one bit. So what we want to do is we want to talk about what that parent function looks like. Well, for exponential, our x, what is changing is the exponent, hence exponential. So we're going to have some base, and our bases are always going to be greater than 1. That's going to show exponential growth. If our base is less than 1, it's showing decay, which is going to kind of mimic like a reflection over the y-axis, but we'll see that later on. Most of the time for right now, our bases are going to be greater than 1. So like I said, it's going to be showing growth. So we're going to have some number raised to the x power. That is the parent function. Okay, so that means that there's no one set pattern of going, right 1 up 1, right 2 up 4, whatever, like we did for quadratics or cubics or anything like that. However, we know that it's going to be based on what our base number is. The most popular bases we're going to be using are like something like 2. So you'll see 2 to the x power, e to the x power, or sometimes 10 to the x power. Those are just like the most popular that you see kind of moving forward. But today we'll be using a variety of different bases. E, if you don't already know, is a number in math. It's kind of like pi. The number E is sometimes called the natural number, but it stands for Euler's number. So Euler is actually spelled E-U-L-E-R, Euler's number. It is a constant, mathematical constant, and it's approximately, we use 2.7 as the approximation. So E is about 2.7, just like we say pi is about 3.14, okay? So we're going to be using that number E today, and we're going to talk about it a little bit more in depth in the next lesson, all right? So what I wanted to kind of go back to is getting that chart, getting that pattern of graphing. Well, we know that no matter what we plug in for our base, if we raise it to a power of 0, if x is 0, anything raised to the 0 power is always 1. So that's going to be a point on pretty much every graph, 0, 1. And I'll explain how that changes. If our exponent is 1, then anything raised to the first power is just that number. So whatever our base is raised to the first power is going to give us our base. If we have a 2 for the x, then that means it's going to be our base squared. So whatever our base is squared. Then if we use some negative values for x, if I use -1, remember I'm going to take the reciprocal, so that's 1 over the base. And then of course a -2 would be 1 over the base squared. Okay, so if our base is bigger than 0, we are going to get that exponential growth, and it's going to look something like this. 0, 1, 1 to a number bigger than 1, and then 1 to a number bigger than 1 squared, and then -1 would be 1 over, and then so on and so forth. They would get smaller and smaller and smaller. As you can tell, we are going to have a horizontal asymptote for this graph because anything raised to a power will never give us a value of 0, right? I can't have some number raised to a power and get 0. It's just not possible. So that's why we are going to have a horizontal asymptote here at 0. So using this graph, we can easily figure out our characteristics. Domain for exponentials will always be negative infinity to positive infinity. We love when that happens. Range, obviously the y values from bottom to top. The lowest y values that we're going to be getting here is 0, but remember we don't include that value. We're going to get closer and closer and closer and closer to 0 without touching, and then obviously all the way to infinity. Where is this graph increasing from left to right? The entire thing. Where is it decreasing? Nowhere. Where is it positive from left to right? The entire thing is. Where is it negative? Nowhere. Does this graph have any kind of symmetry? Not at all. And do we have an asymptote? Yes, we have a horizontal asymptote at y equals 0, okay? Pretty much every single exponential function that we're going to deal with is going to have a horizontal asymptote. When we get further into our unit and talk about logarithms and the graphs of those, they're also going to have asymptotes, but not necessarily horizontal ones. And then our end behavior. As your x approaches positive infinity, those y values are also approaching positive infinity. But as our x values approach negative infinity, our y values approach 0. They're getting closer and closer to 0 without touching. So here's our general parent function. Remember, noticing that our base is greater than 1. If our base would not have been greater than 1, it would have looked decay. It would have looked something like that. Okay? So then, of course, we go to those transformations chart that we've seen about 8 times this school year. So you should know by now that everything on the left-hand side are all of our horizontal transformations. So shifting right, left, stretching and compressing horizontally, and reflecting over the y-axis. You should know by now that all of those horizontal transformations are affecting the x. So wherever the x is in the parent function, whether it's inside parentheses, whether it's in the denominator, whether it's in the exponent for this parent function, that's where those transformations occur. For this, I am going to use a capital B as my base. And you can see that right here, capital B for my base, because we do describe a horizontal stretch or compression by a lowercase b, and I don't want to change that and confuse you guys. So if I want to show you what a shift right would look like in an exponential function, that means we're going to have some base raised to a power, and then that is our x value. So that means it would be subtracting by some number. So it might be, whatever the base is, 2 raised to the x minus 1 power. So that means my base is 2, and then I would be shifting right 1 unit. If I'm shifting left, then I have some base raised to the x plus some number power. These are going to look the same. My base is going to be raised to the b times x power. So maybe that's like 2 raised to the 1/3 x power, or 2 raised to the 2x power, or something like that. Okay. And then lastly, if I reflect over that y-axis, my base raised to the negative x power. All right, and then of course over here are all our vertical transformations. So they're happening outside of where the x is. So that means they're not happening in the exponent. They're happening either in front of the base or behind what's being raised to a power. So if you think about, something raised to the x power, if it's happening here or here, it's vertical. If it's happening here, it's horizontal. Okay? So shifting up would look like b raised to the x power and then plus k after that. Shifting down, b to the x power minus k. If I am vertically stretching or compressing, that means I have a number times my base raised to the x power. This is separate. This is not the same thing as ab raised to the x power, so just keep that in mind. All right, and then lastly, if I'm reflecting over the x-axis, then I'm going to see a negative b to the x power. Again, there are no parentheses there, so be careful. Okay, so let's go ahead and get started. Before we do, I do want to make one important note. So typically, whenever we transformed a parent function, we would follow a specific pattern of graphing. And the first thing that we would do is we would move our quote-unquote origin by any shifts left or right, and that would be a point on the graph. That's not going to be this case here because 0, 0 is not a point on our parent function. So I can't say, oh, if it shifted left 1 and down 2, left 1, down 2, here's my new point on the graph. There's my new center, or that's my new point of inflection. That's not the case because 0, 0 is not a point on this graph. Now 0, 1, we said was quote unquote always going to be on point on that graph. But if I move that point in accordance to the transformations, it's going to change that point, because if I change 0, 1 and apply a vertical stretch or compression or horizontal stretch or compression, that's going to change the value, right? It's not going to be at 0, 1 anymore. And we know that any base raised to the 0 power is gonna be 1. So we need to keep that in mind. So what we are gonna do is we're gonna almost like shift the entire graph. So we are still gonna use that HK value, shifting left, right, or up and down, but that's just gonna become our new origin. It's not gonna be a point on the graph. So we'll get to that whenever we start sketching. First, I just want us to identify who the base is, what the transformations are, and domain and range, and then we'll do the same thing but graph it. So what we want to do is determine who the base is. So remember, the base is what's going to help us with these values here. Okay, those numbers are not always going to be the same. It depends on what the base is. So the base is what's being raised to a power. In this first problem, our base is 7. The transformations, the only transformation I see is the x plus 1. That's in the exponent. You may be tempted to say that 7 would also be a transformation, like maybe a vertical stretch or something like that, but that's just the base. We don't care what the base is. I mean, we do in regards to graphing, but as far as transformations go, it doesn't matter what the base is, okay? So our transformations, I see a plus 1 where the exponent is, so that means I'm shifting left 1 unit. Domain will always be negative infinity to positive infinity, and then range is going to be based on shifts up and down or reflections over the x-axis. Well, we have none of those transformations applied, so it's still going to be from 0 to infinity. Okay, let's try this second one. So remember, our base is what's being raised to a power. What's being raised to the power is e, not 3, not 3e, but just e. So remember, e is a number. It's about 2.7, but we can just put e as our base and then list out our transformations. I don't see any horizontal transformations because nothing is affecting my exponent. I do see a 3 in front, so that's a vertical stretch. And then I do see a negative 5 at the end, so that means I'm going down 5. So domain, again, always negative infinity to positive infinity. My range, because I've shifted down 5, that means I'm now starting at that negative 5 and then going all the way up to infinity. So if you kind of come up here and imagine this being shifted down 5, it would look something like this. Range, negative 5 all the way to infinity. Okay. All right, that vertical stretch doesn't affect domain or range. It would obviously affect the graph, but not domain and range. And then the last one, what's being raised to a power? The base is 3/4. Now, earlier we said we were going to be dealing with bases bigger than 1 because that was showing exponential growth. Well, this base is a number that's less than 1, so it would be showing exponential decay. So if we had to sketch this graph, it would not be going up from left to right, it would be going down from left to right. And even if we didn't recognize that, if we followed the pattern of 0, 1, 1 base, 2 base squared, negative 1, 1 over base, we would see that and we would get that graph. Transformations, I do see something that's horizontal because I see a 4x in the exponent, so that means it's a horizontal compression. Remember, numbers bigger than 1 are a horizontal compression. And then I see a plus 1 at the end, so I am going up 1. Domain, negative infinity to positive infinity. Range, this time I've shifted up 1, so from 1 to infinity. All right, so now that we know how to recognize, let's go ahead and recognize and then sketch. So we're going to sketch. We are going to find the domain and the range again. I'm also going to add in behavior. And so I want us to identify what our base is, list out our transformations, and then figure out the pattern of graphing, and then domain, range, and behavior. Okay, so first things first is, what is our base? Our base is 2. What are our transformations? Well, there's a negative in front, so that's a reflection over the x-axis. There's an x plus 3 in the exponent, so that means I'm going left 3. And there's a negative 1 out back, so I'm going down 1. So that means, how do we start to graph this? I am moving my entire coordinate plane, you could think of like moving the grid, moving the origin, left 3 down 1. So if I go left 3 down 1, I'm going to use like an X or sometimes a star because I need to notate that that is my new origin, but that is not a point on my graph. Okay, so that just means my starting point, quote unquote, is going to be from the -3, -1. From that point, I'm using my pattern of graphing here. Okay, so 0, 1 is always going to be a quote unquote point, 1 comma whatever the base is, 2 comma whatever the base squared is, -1, 1 over base, etc., etc. Well, my base is 2. So I am going to have 0, 1. I'm going to have 1 base, so 1, 2. I'm going to have 2, whatever the base squared is, so 2 squared, which is 4. I'm going to have -1, 1 over the base, and then -2 is 1 over the base squared. Now, you don't have to put all 5 of these values. A good graph will have 3. For this graph, exponential, a good graph will have 3. Other graphs, I always want it 5, but sometimes it's good to list out these 5 and then graph whichever ones are the easiest to give you a sense of how the graph is transformed and what it looks like. Because as you can expect, we are going to get a lot of fractions and small numbers and big numbers, et cetera, depending on our transformations and what our base is. So we need to keep in mind what transformations have we applied. We have only applied the left 3 down 1. We have not applied the reflection over the x-axis. So how do I do that? Well, if I'm flipping something over the x-axis, it is affecting my y values. It is a vertical flip. So instead of going 0, 1, it's going to be -1, 1, -2, 2, -4, -1, -1/2, and then -2, -1/4 if I want to plot that point. So now from this point, we plot those values. What's another good thing about this asterisk that we get from the beginning, we always know that that is where our horizontal asymptote is going to go through. So that's kind of giving you 2 really important things, that shift left, right, or up, down. It's giving you your new origin, and it's also going to give you your horizontal asymptote. So from that asterisk, I want to go 0, -1. I want to go 1, -2. I want to go 2, -4. 2, 3, 4. I also can go -1, -1/2, and if I wanted to, -1, -1/4, which is going to be very hard to graph. But now we get an idea that our exponential function looks something like this. Okay, domain, always -infinity to +infinity. Range from bottom to top, -infinity all the way up to that horizontal asymptote, which is at -1. And then I also want to write out our end behavior. As your x's are approaching infinity, your y values are actually going down to -infinity. As your x's approach -infinity, those y values are approaching that horizontal asymptote, which is at the -1. Okay, let's try it again. Okay. Now we're going to do the same thing. Identify the base, the transformations, sketch, and then domain, range, and behavior. This time our base is E. So our base is E, which is approximately 2.7. Okay, our transformations. Oh, I noticed something. When I'm going to look for those transformations, I see a lot of horizontal transformations. Hopefully by now in your brain, you have programmed to know that anytime you have a B value, if there's something in front of the X in transformations, you have to factor it out. So if I rewrite this, my base does not change. My B value doesn't change either. I'm just going to factor it out. So I'm left with X minus, what is 3 divided by 1/2, or 3 times 2, 6. And then I still have the +1. So really my transformations, I do have the horizontal stretch, but I am going right 6, not right 3, and up 1. So that means I'm starting from right 6, up 1. This is my new origin point. This is my new horizontal asymptote. So from that point 6, 1, so from 6, 1, I know I want to go 0, 1. I want to go 1, whatever the base is, which is about 2.7. 2, whatever the base squared is. Now, obviously, you could use a calculator for this, but that's about 7.3. Negative 1, 1 over the base. So 1 over that 2.7 is about 0.37. I'm obviously not going to do negative 2 because that's going to be a really small number. Okay, so this is plenty enough information. I want to make sure that I've taken care of all of the transformations. So far, I have only applied the right 6 up 1. So I've left out the horizontal stretch, so now I need to apply that. Horizontal stretch, so I'm dividing by 1/2, aka multiplying by 2 to the x values. So 0 times 2 is still 0. Let's change colors. 1 times 2 is going to be 2. 2 times 2 is 4. And negative 1 times 2 is negative 2. So, now from that point, that asterisk, from 6, 1, I'm going to go 0, 1. I'm going to go 2, 2.7. So 2, 1, 2.7 would be like somewhere here. I could also go 4 and up 7.3. I know that's going to be off the graph, but 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7.3 would be somewhere like up here. And then I could also go left 2 and then up the 3.7. So about like right there. And so again, you get that shape of that exponential. It is growth because e is a number bigger than 1. Our domain, still negative infinity to positive. Our range, this time from bottom to top, it's starting at that horizontal asymptote and going to infinity. And then in behavior, as your x's approach infinity, your y's are approaching infinity as well. And as your x's are approaching negative infinity, your y values are approaching that horizontal asymptote of 1. Okay, this would be a great time for you to pause the video and try the last 2 on your own if you think that you're ready for that. Okay, so like we always do first is identify our base. So here, what is being raised to the exponent is the 4. So we have definitely a lot more transformations in this one, but our base is 4. Our transformation, so starting from the beginning, I see a negative. So that means I reflect over the x. Then the next thing I see is the 1/2, which is a vertical compression. The next thing I see is the negative in the exponent, so that's a reflection over the y. And then the last thing I see is the positive 2, so that means I'm going up 2. So the only left, right, up, down I have is a positive 2. So that means my new starting point is here. So that's where my new horizontal asymptote is. Okay. So from the point 0, 2, remember we always follow this pattern of 0, 1, 1 base, 2 base squared, negative 1, 1 over base, and then negative 2, 1 over base squared. Okay. That last one might be a little bit harder to graph, so you can write it down or leave it off, whatever. But now I want to make sure that I don't have any other transformations. Well, obviously I do. I have the reflection over the x, so let's do that first. So I have a reflection over the x-axis, and I actually had that horizontal compression that I could probably do both of them at the same time. So reflection over the x-axis is going to change my y values from positive to negative. So now obviously that would be a negative 1, negative 4, negative 16, etc., etc. But there's also that vertical compression of 1/2. So all of these are going to be multiplied by a negative 1/2. So now this is negative 1/2, negative 2, negative 8. This would technically be a negative 1 over 8. And then this obviously would be a really, really small number. So we're not even going to worry about that last one. You could do the math to find where it would be, but I wouldn't suggest graphing that because it'd be very hard. So that's taking care of this, and we've already done that. And so now we just need to reflect over the y, which is going to change the sign of the x. Well, 0 is not positive nor negative. Now this is going to be a negative 1, a negative 2, and a positive 1. So from that asterisk, from that point 0, 2, I want to go left or right 0, down 1/2. I want to go left 1, down 2. I want to go left 2 down 8, 2, 4, 6, 8. And then I can go right 1 and down 1/8, which is obviously very hard to graph, like I said earlier. And then again, we get that shape of our exponential graph. So here we are, domain, negative infinity to positive, range, lowest to highest. And then in behavior, as x approaches infinity, those y values are approaching that horizontal asymptote. As x approaches, negative infinity, the y values are also approaching negative infinity. All right, and here's our last problem. Okay, so identify the base. This time our base is 1/2, so it is going to be another decay, if you want to think of that, because anytime your base is less than 1, it's a decay, greater than 1, it's a growth. Okay, but we also have some transformations. So our transformations, the first one I see is that 3 in front, so that's a vertical stretch. I see a -2 with my exponent, so that means I'm going right 2. And I also see a -4 at the end, so down 4. So that means my new starting point, right 2, down 4, right 2, down 4 is here. So that's my new horizontal asymptote. Okay. So from the point 2, -4, I want to follow my pattern of graphing. Always 0, 1, 1, whatever the base is, 2, whatever the base squared is, -1, 1 over the base. This time -2 might be beneficial to us because it's 1 over the base squared, which is going to be just 4. So then now I want to also take care of that vertical stretch. That vertical stretch is by a factor of 3. So everything in the y column is going to get multiplied by 3. So this is now going to be 3, 3/2, 3/4, 6, and 12. Excuse me. And so from that asterisk, from that starting point to -4, I can go up 3. So 1, 2, 3. I can go right 1 up 1.5, right 2 up 3/4, left 1 up 6, so 4, 5, 6, and then left 2 up 12, which, will it fit? Left 2 up, 4, 8, 9, 10, 11, 12. Yes, perfect. And so we see that shape come into play. So remember we said this was going to be a decay, and we only stretched vertically and shifted left, right, up, and down, so it didn't affect the shape of the graph. It's still showing that decay. It's not showing a growth. Domain is still going to be negative infinity to positive infinity. Range from bottom to top, that's going from -4, or horizontal asymptote, to infinity. And then in behavior, as x approaches infinity, the y values are creeping towards that horizontal asymptote of 4. And as x goes to negative infinity, the y values get bigger and go to infinity. Okay, so make sure you understand where your base is located, how it affects the graph, where transformations are, how they affect the graph, and then just study this pattern that it's always 0, 1, 1 base, 2 base squared, -1, 1 over the base, -2, 1 over the base squared. We'll talk more about this number in our next section, but that's about it. Great job. Thanks.